Hello everybody. So as I mentioned last video, I will make this video for discussing a couple of points that are important to be clear for you when you do the calculations of the heat of reaction method. The first point is regarding the procedure that we're following, and there is a slight difference between what we did or what I discussed in the previous video and what is in the textbook. So I'd like to go and just go through the procedure in the textbook. So this is the first method, which is the heat of reaction method. And by the way, you would see the I'm not sure where is it, but it's somewhere here, which is the procedure. Yeah, I think we will come to it later. But anyways. So here you would see, no, it's not this. I'm sorry, just going to, yeah, okay, so this is the procedure. So this is the first method, which is the heat of reaction method. You would see here, this is the same procedure that we mentioned or discussed last time, the mass balance, and the second, which is the important point, which is choosing a reference state. And this is a point that I mentioned in the previous video, and I told you that I will make a comment on this on the coming video. So the way we did the calculations was we suggested the hypothetical path, and based on the hypothetical path we made the calculations. And we also had the same table like the one we had here. The main difference, and I would like to see the yeah, this is the hypothetical path. The main difference between what we are doing and what the textbook is making, which is not going to affect the final answer, but just to make it clear for you in case you check the textbook and find there are some differences. That what I did is I followed this hypothetical path as it is, which means that I got the change in enthalpy from the reactant's temperature to the standard temperature, or the reactants at the standard temperature. So this is what I did. And for the products, it's the same thing. We calculated the enthalpy difference between the product at 25 to the product at the outlet temperature. So this is what we did. In the textbook, the way they are doing the calculations is that they are calculating, and let me go back here. They are calculating. I want to find the exact sentence. So this is the the reference state, and this is the inlet outlet. Oh, and now the stream enthalpy. So this is the H of the two streams is going to be the enthalpy of the stream with relative to the standard temperature. So, for example, this H2, which we calculated as the enthalpy change from the 300 to 25, the textbook is putting this as the enthalpy at 300 relative to 25. So it is negative what we did. The only difference is that we put the limits of integration from 300 to 25. The textbook is putting this the other way, from 25 to 300. This applies for H2 and H3. So if you check the values of H2, of course H1 is 0 because it's 25 to 25, so it doesn't matter which is before, or which is the first and which is the second. But for H2 and H3, we had the negatives of these, of negative 8.47 and negative 8.12. So this is the main difference between what I did last time and what the textbook does. So that's why you'll find these negative. So will this affect the final answer? The result, or the answer to this question is no, because the way the textbook or the equation is written in the textbook for calculating delta H is the extent of reaction plus the multiplied by the standard heat of reaction plus the summation of N out multiplied by H out, which is the same. These two terms are the same, and this is the negative of ours, so it's minus. So it's going to be plus. So at the end of the day, what we did is we put negative of this term, and we put a positive sign here. So it's positive of the negative of this, which is going to be the same. So at the end of the day, what we did and what the textbook is doing is giving the same results. There is kind of a good validation for the two approaches. So the validation of this approach that is done in the textbook is that they are following the same or they're writing the equations the same way we wrote it in chapter 8. That delta H is in out H out minus in multiplied by H in. So it is the same delta H as before. The only difference is that we included the term of the extent of reaction. So it's exactly the same thing we did in the mole balance or the mass balance before. In the mass balance we said out equals in for non-reactive systems, and for the reactive system we said out equals in plus the extent of reaction multiplied by the stoichiometric coefficient. So it's exactly the same thing, and that's why I think this is very nice to do, because it follows the same procedure. If you don't have reaction, this term is going to be 0, so we will end up with the same thing. For the approach I'm doing, or the reason I'm doing what I'm doing, is that I like to follow the hypothetical path. By this I mean that the hypothetical path is saying that we are changing the reactants or the temperature of reactants from this temperature to 25. Then I add this, so it's the same approach we do with any hypothetical path before. And if you remember what we did in chapter 8, this is exactly what we did. We assume a hypothetical path, and based on the hypothetical path we do the calculations, and we add the enthalpies of each one of the segments in the hypothetical path. So this is why I prefer to do it this way. Anyways, you prefer this way, I'm suggesting you prefer the textbook's method. Both are going to give you the same output, as long as you are using the proper equation with this. And in the approach I'm assuming, or I'm proposing, we add the three enthalpies. In the textbook you add these two minus this. So it's fine. Whatever thing you like is going to be okay. It's up to you, as long as you do the calculations correctly. So this is the first point. The second point is a question that is a very valid question that I found some of the students asking, which is why do we include inerts in the calculations of the reaction? Which is a very valid question. This is the type of calculations that we are doing for reactive systems, and the reason we are going through all this procedure is that we have reaction. So if I have an inert, why, like nitrogen, why do I take nitrogen into consideration? Why do I take nitrogen in calculation of H1 and H2, although it's not part of the reaction? And this is a very good question, and the answer to this question is very simple. That but before answering this question, I would like to remind you with what we did. So for the nitrogen in the feed, we changed the temperature of nitrogen from 300 to 25, which was calculated using this equation, the integral of Cp dt from 300 to 25. And for the product, it is from 25 to 1000, which is the integral of nitrogen from 25 to 1000. And we added these two terms at the end. When we did the calculation of delta H, we added the two things. So when you combine the two equations, it's going to be from 300 to 25 and then from 25 to 1000, which mathematically, this term from mathematics, you can break this into two parts, from 25 to 300 and from 300 to 1000. So this is the same as this. This is mathematically correct. This is a mathematical rule that you can break the limits of integration into two or three and add them together. So if you look at this term and this term, they can cancel each other. From 300 to 25 is the negative from 25 to 300. So it's going to be at the end of the day from 300 to 1000. So this means that you can exclude nitrogen from the calculations. This is what the mathematics is saying. Instead of doing the two integrations and doing the calculation of enthalpy of nitrogen in the feed and the enthalpy of the nitrogen in the product, you can directly assume that nitrogen is an inert that is not part of the reaction, and calculate delta H for nitrogen separately and add it to the rest of the delta H terms. This is something you can do. So we do the calculations for nitrogen as non-reactive system. You can also do this for the excess reactant. because the excess reactant is not part of the reaction. So you can do this for oxygen. We had 600 moles of oxygen in the feed, 500 were consumed and 100 was not consumed. So the 100 moles of oxygen followed the same thing. We did the delta H for these 100 moles from 300 to 25, and these delta H for oxygen in the product from 25 to 1000. So the same thing, we can break this into two, and you can get the delta H for the excess oxygen. So this is clear, the excess oxygen, that this applies only for excess oxygen, and then you can calculate delta H for the excess oxygen as an inert that is not part of the reaction. And of course this will save time, because you wouldn't do the integration twice. In the case of oxygen and nitrogen, we already had table B8, so we can directly go and pick the numbers from the table, so it's not a big deal. But for other materials or gases that are not in the table, we need to do the integration manually, and this would be a big time saver. So now comes the question, since what we are doing is going to end up with this one integral instead of two, why do we do this? We do this to make the procedure systematic and to reduce the possibility of mistakes. The reason of what I'm saying is that you saw the calculations are long and they take a lot of time. And when you try to make the calculations, or when you do the calculations, we try to minimize the sources of error as much as possible. You have a possibility of picking wrong numbers from the tables, picking wrong boiling points in case you have phase change, picking the wrong inputs from any table. So there is a big possibility of making mistakes. So as much as we can, we are trying to make the calculations systematic. If you are sure that you can do the calculations without having any issues with messing up the numbers, multiplying this delta H with the wrong number. And for example, in this case, you have to make sure that you multiply this delta H by 100, not 600. So you have two numbers for oxygen. You have three. You have 500, you have 100, and you have 600. The 500 is what you are going to include in the reaction, and for the 100 is the excess, and 600 is the total feed. So if you can make the calculations without having any confusion, without putting a number instead of another number, I would definitely suggest you do this. Exclude all the inerts, all the excess materials, and include only what you have in the reaction in the hypothetical path, and get this shortcut for these non-reacting materials to calculate their delta H. If you think you will mess up the calculations, you would get confused, things would be not very clear for you, just follow the path, follow the hypothetical path for all the materials in and out. It's gonna take longer time. It's not very long time, more than what it already takes, but it's going to be more systematic, and will reduce the possibility of making mistakes. So this is the point that I want, the 2 points I wanted to make. So yeah, these were important points. That's why I wanted to discuss with you before moving to the next method, which we are going to discuss next time, inshallah, which is the heat of formation method. So I'll see you next time, inshallah. Goodbye.